Welcome to today's class. Our topics today will include LTE Advanced, as you see behind my back right now. Basically, I'm going to conclude the overview of LTE 4G, and then I will tell you what we know as of today about the 5G new radio technology. And then we'll move forward to what we call the vehicular use case. The vehicular use case, the connected vehicle problem. And as you shall see, it still has got to do with LTE, because basically what we talk about when we talk about connected vehicles that are operating under a cellular coverage is we are talking about a specific feature that has been designed and standardized for LTE since release 12, and that is a device-to-device communication. Because at the end of the day, what we are talking about when we look at connected vehicles are vehicles that, among other features, are talking to themselves. So in a way, we need to enable this communication paradigm by having a device-to-device communication. Whereas in LTE and in all cellular networks up to this day, the typical paradigm has always been device to network, network to device, and never device to device. So that will be for the second part of today's class. But let's start with LTE Advanced. So you've seen yesterday the physical layers and the upper layers of LTE. Now LTE Advanced is an improvement of the baseline LTE. And LTE Advanced, as shown in this timeline, has started with release 10 and has gone on until the last LTE related release, that is release 14. As we said yesterday, all of these releases are currently in a frozen state, so we know basically what's in there. What is important to understand about LTE Advanced is that LTE Advanced is not so much a modification of physical layers or upper layers of LTE. Yeah, there are some refinements there as well. But mostly it is about network densification. And as you see, especially in release 12, you have the title of the release that is small cells and network densification. Network densification basically means bringing more capacity to the network. Bottom line of network densification is you add small cells. When you add small cells, as we also introduced yesterday, what you're doing is you're adding more local capacity to networks. You make more resource blocks available in small areas. And if you have many of these small areas, imagine a patchwork of small areas all over a larger campus or a larger city area. And what you're doing is you're enabling people who are in those areas to have more resources, because you have these small cells that have low power and do not cover a large area. And so whatever resources they are using in a restricted cell may be reused in nearby cells. So network densification is all about having small cells coexist with larger cells and reusing resources. Reusing resources in nearby areas by having low power transmission from these cells, and in this way you avoid conflicts between resource blocks that are operating on the same frequencies. I just want to expand a bit on this by introducing three of the main features that LTE Advanced has standardized starting from release 10. I'll just touch briefly upon these. They are carrier aggregation and high-order MIMO and network densification, as I was saying before. Carrier aggregation, remember that what I told you yesterday about LTE, that LTE has in its baseline standards just 20 megahertz channels. Now, 20 megahertz channels are large size of bandwidth if compared to previous standards. The point is that when you have 20 megahertz, okay, you can start assigning resources to users, but then you always end up with some leftovers at the edges of these spectrums, that if you need to assign these leftovers resources to users who need a large bandwidth because they are streaming a 4K video or they are transferring large amounts of data, then you just can't do it because these leftover resources are too little. But then you may have, and usually operators have more than one chunk of 20 megahertz on the spectrum. But in LTE, they can't assign resources to users if these resources are coming from different portions of 20 megahertz spectrums. Well, LTE Advanced changed that. Changed that by introducing carrier aggregation. And carrier aggregation is, okay, if I've got some leftover resources that are not used in one interval of the spectrum, then I may assign these together with other resource blocks on another portion of the spectrum, a nearby portion of the spectrum that is not contiguous. And this is the one of the major advances in LTE Advanced because it allows a better use of the spectrum. So basically you end up using up to, what the standard says is you can aggregate bandwidths up to 100 megahertz. Of course, getting chunks, what previously were 5 chunks of 20 megahertz, now you can aggregate them even if they are in different portions of the spectrum. One problem you have to deal with, however, is if you are aggregating resources from chunks of spectrums that are on different frequencies, like, you know, you said yesterday that LTE uses 800 megahertz, 1,800 megahertz, and 2,600 megahertz. Well, if you have these, then of course you have to deal also with different propagation conditions. So assigning to the same user at the same time a portion of resources that come from the 800 megahertz spectrum and that come from the 1,800 megahertz is not so easy, because what you're doing is you're asking it to deal with different power levels, first of all. And so the design of the receiver turns out to be more complicated. Another feature that is introduced by LTE Advanced are higher order MIMO. Higher order MIMO in LTE Advanced is still from the transmitter, from the E node B to the UE, because higher order MIMO requires large size antenna. So it's something that usually you have a hard time fitting inside a small handset. And so it's, again, this is an evolution that is mainly targeted to transmission from the E node B to the UE. And what they introduce is 4 times 4 and 8 times 8 configurations that may be used either for a single user. Of course, the single user must have a device that is capable of receiving a 4x4 and 8x8 MIMO transmission, or you may have multi-user MIMO. In this case, even if you have 4x4, you can do a 2x2 for one and 2x2 for the other, or 8x8, you can have parallel transmission to up to 8 users. And then the other issue, as I said before, is network densification through so-called multi-tiering. Multi-tiering means creating different superimposed coverages. The idea is to have, well, let's start from the bottom. You try to incorporate in LTE, and this is going to be a feature of 5G as well, incorporating in the cellular network also Wi-Fi coverage. But just to look at LTE Advanced, you usually have either femtocells. Femtocells are small cells that are given by operators in home environments. So the operators sometimes have these business models where they give users femtocells to use at home. Femto is a terminology that identifies something that is very small. So very small cells that you put in your home instead of Wi-Fi. What is the good of it? The good of it is that you have your own cellular cell, your own operator cell in your house, so you can use your cell phone and you're always connecting to your cellular operator in your house. By doing this, the cellular operator offloads the nearby cells that may be used at this point, may be used just by people who are traveling or passing by in that area, but they are not used by residentials who are instead exploiting their femtocells in their homes. So the residentials have good coverage, they have high bandwidth, they have a cell that is basically just for themselves and for their family members. And the cells in the area where these femtocells are placed, the other cells are offloaded. So they may enjoy higher capacity because of this. Then there is the case of picocells. Picocells are not home cells, they are public cells. They are usually found in areas where you have large gatherings, such as stadiums, squares, shopping malls. In these areas, or airports, in these areas, you need to have a very densified coverage because of the large number of people that may be going about specific times usually. So in stadiums when there's a game, or in a shopping mall during the opening times. And normally what you do is you have a large cell, a so-called macro cell. It's at the bottom here. You can probably read it because it's white and yellow. The macro cell covers these areas during 24 hours a day, so all around the clock. And then when you have an event, like a match, or during the opening hours of the shopping mall, you activate these picocells. And these picocells offer extra coverage and offload the macro cell during this time. Between the difference, of course, between femto, pico, micro, and macro is the power. The power and, of course, the coverage radius. Here you have on the left-hand side the ranges of powers that are allowed. Indoor, there's a regulation that does not allow antenna powers to be higher than 100 milliwatts. So this works for Wi-Fi, this works for cellular networks. You can't transmit at higher power because of safety and health concerns. But you may use in larger areas, there are shopping malls, for example, you may have picocells. In this case, the indoor power is up to 250 megawatts. And then, of course, outdoors, that's tens of watts. And these are for micro and macro cells. So this multi-tiering means really going after the density of people by placing there an appropriate size cell that caters for sudden surges in number of people that may be in that area. Now, the problem with network densification and this multi-tiering is you have to deal with interference. Normally, what UEs do, they associate, or as the terminology goes, they camp on the cell with the strongest signal. So even if you are in an area where you have a double coverage, you have a small cell or a picocell, and then on top you have a macro cell, your terminal will camp with the cell with the transmitter that in the place where the terminal is has the highest received power. So in this example here, you see there is this blue tower, and this is the path loss seen by the power transmitted by this blue tower, and this green tower here, and this is the path loss. In the area closest to the blue tower, and this is the case of this terminal here, this terminal will camp with the blue tower because this is the highest received power. In this area on the border, then it's not so clear because, of course, power fluctuates. There's fading, as you know, and especially if you are close to the edge. And this is a problem that operators often face, but they have been facing this since the time of 2G. The cells will select one cell for a while, then they will move to the other, and then they go back to the other cell. And this burdens the network a lot, because every time you switch cell, you add signaling traffic, which is basically useless, because at the end of the day, you end up just moving between two cells that have an almost equal, that are offering almost equal power. But anyway, this is something that has been known by operators, and what operators do is every time you associate to a cell, they have a sort of hysteresis that prevents going back to the previous cell for a while, or they prevent going back to the previous cell unless the margin between the two received powers is higher than the threshold. But now with multi-tiering, we have even another problem. The other problem is that if you have a macro cell and you have a picocell nearby, then it is true that when you are on the edge of the picocell coverage, you may still be camping with the macro cell. So the edge of the picocell is really hard to define, and if you have a macro cell nearby, the edge of the picocell ends up shrinking more and more, because the macro cell is more powerful and may, even though the picocell has got a certain power, it can go above 100 milliwatts. So this may shrink the coverage of the picocell and effectively reducing the usefulness of picocells. So release 10 introduces a couple of features that try to counter this problem. They are called cell range extension, CRE, and together with it, a feature called almost blank subframes. Let's see what they are. So, as I said, one of the problems that you have with this multi-tiering is when you have a terminal that's close to the picocell, then let's call it the inner picocell user, then everything is fine. When you have a user that is in the outer cell, the outer picocell, then likely it will associate to the macro cell. But it's not only that. It's also that once you associate to the macro cell here, when this guy that I'm pointing at uses uplink resources to communicate to the macro cell, due to its distance, it needs to transmit on these uplink resources at a very high power. This will conflict with with resources that are associated to uplink transmissions in the picocell. So what you're doing here is you are interfering with the same resources used in the uplink, because this one that is on the border of the picocell needs to use them to transmit to the macro cell. And since it's very far away, its transmission is very powerful. And this interferes with the same resources used by this guy who's trying to talk to the picocell. So for this reason, to avoid this problem, what you're doing is you add a selection offset. Basically, you trick the outer picocell user into believing that the picocell is strong, has got a stronger signal, even though it doesn't. You just artificially add an offset to the received power so that the algorithm that selects the camping to one cell will force the outer picocell user to associate to the picocell. In this way, even though the macro received signal is higher here, you still force the picocell user to associate to the picocell. And of course, this solves the two problems, because now we have a larger control on how large, we have a finer control on how large the picocell coverage is, because what you're doing is you are artificially increasing as much as you like. The offset may be played with, and indeed the offset is advertised by macrocell, by the macrocell. What the macrocell is doing is it advertises the offset to all users in its area, saying, okay, if you are under this coverage and you hear a picocell, then the picocell will you should add an offset to this picocell so that you can associate to the picocell rather than to me, and in this way we avoid this problem. Okay, but now we have another problem. Now we have another problem because when we do this, this guy here will not interfere in the uplink with all the other inner picocell users, but it will be interfered with by the macrocell in the downlink. Because now, even though we may have tricked, and this was just a dirty trick to have a better association, a larger coverage of the picocell, but even though we may have tricked with an offset the outer picocell user, still the received power can't be changed. So what you are seeing, what this guy is seeing here is stronger power coming from the macrocell than from the picocell. So when the picocell is sending data in the downlink to the outer picocell user, this data may be interfered with by the macrocell on the same resource blocks. And for this reason, what the standard suggests is a procedure called almost blank subframes. The idea is the macro cell will lower the power of that it uses to transmit in specific subframes, and it will tell the picocell what these subframes are, and these subframes will be used by the picocell for the downlink transmission. So the macro cell will not completely refrain from transmitting during those subframes. What it's doing, it's lowering its power. In this way, the macro cell will assign these downlink resources where you have these almost blank subframes just to users that are nearby the macro cell and are capable of hearing these reduced power subframes. And it will tell the picocell, look, in these subframes I am transmitting at reduced power. You can use the subframes for your downlink transmission. Okay. In this way, what we have is we are sort of micromanaging the users of the macro cell. Since, mind you, the macro cell knows where users are, because the microcell localizes users. So we as a macrocell know where our users are, which directions they are, how far they are, and of course the macrocell knows where the picocell is, because they are the same operator. So if the macrocell detects that one user, the picocell is there, and you have one user here, fine. The macrocell will assign to the user here that's far away from the picocell these low power resources to this user close by. Is close by, so it doesn't mind receiving low power subframes. These same low power subframes will be transmitted also in other directions, and they will also be transmitted in the direction of the picocell. If I have users nearby, close by, I can serve them, but the ones in the picocells will not be affected and interfered with by this picocell, by the macrocell almost blank subframe. So in this way, the aggressor macrocell creates protected or downlink subframes. It's switching off. In reality, it's not switching it off. It's lowering the power. In this way, it can still serve some users. Okay, I just got a couple of slides here to conclude what we know of what the 5G physical layer will be beside what I've told you so far. What I've told you so far applies to 5G as well. So 5G as well is LTE Advanced. There will be the same densification. Actually, the densification in 5G will be even more extreme. So all of the procedure outlined before, the enhanced interference management, the almost blank subframes, they will be used in 5G even more so. The physical layer doesn't change much. One of the differences we'll see in 5G is a different use of spectrum. There will be other portions of the spectrum that are going to be used. I told you yesterday that we don't know exactly for sure what these portions will be, because they will be consolidated in 1919 at the World Radio Conference. And until then, what we know is we are certainly going to have portions of spectrum that go up to 100 gigahertz. There is definitely going to be, and I'm willing to bet that there will be a portion of spectrum around 28 gigahertz, because many manufacturers are already preparing prototypes and pre-commercial releases of new radio devices that are working at 28 gigahertz. So that's likely to be one portion that is being considered. There are other portions around the 60 gigahertz spectrum. And these are the so-called millimeter wave coverages. These are especially useful for network densification because they create really small cells. And by operating at 50 gigahertz, you have drastically decreasing power, as also at tens of meters away from the base station, from the E node B. So you can really create small cells, and you increase the coverage a lot, and you increase the capacity a lot. There will also be, and they are considering, transmission in unlicensed spectrum using cognitive networking techniques. What is unlicensed spectrum? It's 2.4 gigahertz, 5 gigahertz. There are other unlicensed spectrum portions here and there. Unlicensed means that the operator doesn't have to pay a fee to the government, usually, to use those portions of spectrum. But of course, these portions are really coveted because think about Wi-Fi. Wi-Fi 2.4 gigahertz or 5 gigahertz. Almost everywhere you go nowadays, you find some Wi-Fi transmission. But this portion may be used where there's no Wi-Fi, like in farm country, and in the countryside or in the mountains. These are good portions, and of course here you need to use techniques that allow you to understand if anyone is already using that spectrum, and this is where these cognitive networking procedures come into place. You basically sample the channel and see if there is a so-called primary user who's already operating on that channel, and if there's not, then you step in and you start using that. Another likely improvement is the adoption of massive MIMO system. The definition of massive MIMO system is when you have a larger number of antenna elements than you have receivers. So massive MIMO is likely to be something in the range of 128 antenna elements, so antenna arrays. There will be in 64 transmit and 64 receive configurations, and we are expecting to see MIMO by UE, of course not 64 by 64 in the uplink as well, but we may see 2x2, 4x4 in the uplink as well, and you'll have a large arrays of antennas at the E node B to accommodate several parallel transmission, even by 2x2 and 4x4. We see other modulation formats. LTE went as high as 265 QAM. 5G new radio is already, there are some prototypes, and I mentioned the other yesterday that a couple of weeks ago we had a demonstration at Politecnico by Ericsson where they had this really large antenna and big receiver, but what they demonstrated were bit rates above 2 gigabit per second, and they were using 1024 QAM modulation, which works very well only if you really have a very favorable SINR. Otherwise, there's no way you can manage to push all the way to 1024 QAM. Okay, this is just a detail. I have not mentioned this, but LTE uses two different ways of OFDM in uplink and downlink. In downlink, it's OFDM as I have explained it to you yesterday. In uplink, it's different. In uplink, it uses something called single carrier OFDMA. There is, instead of using multiple carriers, what LTE is doing in the handset is it's applying sort of additional processing by DFT, a discrete Fourier transform, that let's say brings together all these small subcarriers into one single subcarrier, and then you have to do a DFT processing at the receiver as well. That makes, although this is often preferred for handsets because it requires less power, because the transmission has a smaller difference between the peak power and the average power. It's often more complicated and more expensive to have it also at the node B, and especially when you're looking at the situation where we'll have thousands of node Bs in small areas. So to simplify things, 5G is looking into having the same OFDM, cyclic prefix OFDM, which is what we are using in LTE downlink nowadays. So it will just uniform both downlink and uplink in terms of technology transmission. It will still have TDD and FDD transmissions, and likely this is of course quite the norm with any innovation. You see a co-deployment of LTE and 5G at the beginning. Okay, so this concludes the part on LTE. I would like to ask if you have got any questions about what we discussed yesterday and today before moving on to the next subject. Yes?
What is NR?
Oh, sorry. I don't think I have mentioned it, and I just gave it for granted. Sorry about that. NR stands for New Radio. New Radio is the how confidentially we are calling the new 5G transmission and transmitter and receiver devices. Basically, these two pages here outline the new radio advancement. So, new radio is LTE, but also capable of higher modulations, higher MIMO, different spectrums. So it's here. You're right. It's here and there, but I did not explain it. Sorry. Other questions? Okay. So I'm going to move on to the next topic. So I mentioned yesterday that one of the ways in which standardization in cellular networks moves forward is by looking, first of all, at use cases. So this may look a bit strange because usually you think, okay, well, what I'm going to do is I am going to have the technology and then think about what I can use it for. No, the approach here is, okay, what can I use this new technology for? I design some use cases, and then I create, and I really steer the technology toward serving these use cases. This is what 3GPP has been doing since 3G onward. First, think about the use for the technology, and then you focus on getting the technology right for that purpose. So, as I mentioned yesterday, 5G has been focusing on three specific use cases: massive broadband, machine-to-machine communication, ultra-reliable, ultra-low latency communication. And these use cases, these macro use cases, are further, let's say, are further split into other more specific use cases. One of them is the vehicular use cases. I also mentioned that the 3GPP and the European Union in particular looks at this topic with great interest, up to the point that the phase 3 of the public-private partnership projects will have one set of projects specifically dedicated to the vehicular use case. And this shows a great interest on this topic, and I'm sure that you have been reading lots of media articles, and you've seen presentations also about how self-driven vehicles will be the way going forward. And many automotive manufacturers are today investing a lot into the technology that will allow vehicles to be driven by themselves. There are actually several steps. So the completely autonomous vehicle will be what is called the level 5 vehicle. Level 5 vehicle means you step into the vehicle, you step back, and you don't do anything. It's like you are sitting on a train, and you don't touch anything, and the vehicle does everything by itself, or at most by coordinating with some artificial intelligence servers that are in the network, and will tell the vehicle where to go, what to do, and how to behave and how to react. This is likely very, very far away. So even the automotive sector admits that we may not see a completely level 5 vehicle. There will always be some degree of control, of emergency control, that the user will have on the vehicle. Right now, what we are seeing is, so level 1 is the normal vehicles that we are driving every day now. Level 2 are vehicles that have some additional support, for example, self-braking systems or parking cameras, parking sensors that aid the driver. Level 3, there is already, it's mainly the driver that's driving by himself, but every now and then the driver relinquishes some control to the vehicle. This may be done on highways, for example, and the vehicle may have some features that allow it to keep a safety distance. So you set the speed, but then the vehicle adjusts the speed so as to keep a safe distance from another vehicle. It may have lane centering assistance, so it just keeps the center of the lane by using cameras. But still, the driver is in control. Level 4, the vehicle is in control, and the driver is there to re-get the control if anything goes wrong or if there is some critical situation. Level 5 is you're sitting back, you're drinking your tea, you're reading your newspaper. That's it. I don't know if we'll ever see this, but this is certainly one of the ways going forward. Now, all this can't happen just by having vehicles doing everything by themselves. They need to be connected. And they need to have some relationship with other vehicles. They need to talk to them, know where they are, know what they are doing, exchange information. Because, of course, you can have cameras on board. You can have radars or sensors, but they just go so far toward telling you what the other vehicle is doing. You can see that the vehicle ahead is accelerating or decelerating, but you don't know if it's going to make a turn soon. Instead, if you let vehicle exchange information, not just visual cues, this information may include, okay, look, I am going to this destination and I will make a turn in 200 meters. Be prepared. And the vehicle behind knows that it must not pass the vehicle because this one will make a turn soon. Or the vehicle ahead is just, this is not the case in Kharagpur, but it's just slipped on a patch of ice. And so the vehicle start sending warnings to oncoming vehicles that there is a patch of ice in this location that is specifically identified by a GPS set of coordinates. Or you are at a blind intersection and you don't realize that one vehicle is coming too fast onto the intersection, and it may get into the intersection and you may crash. So this may send a warning to nearby vehicles and the other vehicles will stop. All these things need communication. There have been already some standards that have been put in place by IEEE in the US and by ECE in Europe sorry, for vehicular communication. My colleague tomorrow will talk to you about these, and what I'm going to do today is I'm going to basically continue talking about LTE and how LTE already, starting from release 12 and up to now when we are in release 15, is shaping communication between vehicles to replace IEEE and ECE. And yeah, so one thing is try never to have a 3GPP person and an IEEE person who's working on vehicle standard in the same room, because it's like cats and dogs. They are really, before you know it, they are at each other's throat because they are want to defend their own spectrum. So IEEE has been allocated 5.9 gigahertz spectrum, and now the LTE is coveting the spectrum to have CV2X, what I'm going to explain to you now, and they really hate each other. So they hate their guts. They don't want. If I've been talking to some of them and was really embarrassed at how they were fighting as if they were personal enemies about it. So the discussion may get very, very heated. I'm just going to give you the rundown of what CV2X is. Tomorrow my colleague will talk about the other standards, and will also show you some results that we have been deriving in our research that amazingly show that there is basically no difference between these two standards. So when you look at how you can use these communication technologies to avoid accidents, they both work. So there's not really any reason to fight so hard. Or maybe there is, because of course, since they both work, the winner will get the prize, and the other one, even though has got a very good technology, will not get anything out of it. Okay. So what is V2X? Before, in the introduction, you saw CV2X. C stands for cellular. V2X. V2X is an acronym that means vehicle, from vehicle to anything, and identifies all technologies that are designed to let vehicles interact with its environment. So X may be several things. Maybe another vehicle. So in this case, we have the V2V. It may be the infrastructure. So the vehicle talking to a server that's placed somewhere else. In this case, we are calling it V2I. It may be V2P, vehicle to pedestrian. Why? Well, because pedestrians carry their own handsets and phones. So the smartphone may send out the updated location of the pedestrian. And I know, for example, maybe I'm traveling. I've seen this since I've been in India, traveling on a road at night and having people cross the road at night in a place where there are no lights at all. So I think this is very common everywhere, not just in India, but if you have the capability to let vehicles know that there are pedestrians crossing the road ahead, you may slow down, you may be aware of it at least, and you can avoid them. Of course, this entails that they may be willing to give up their position, and the network will have to communicate to the car that these people are in the area. This includes also bikes and motorbikes as well. So V2X is a vehicle to anything else. What we also V2X is, broadly speaking, either communication between the vehicle and the internet. For example, a vehicle wants to know one specific use case in this area that we are discussing with car manufacturers is, for example, keeping a history of what has happened in a specific area. You may have seen, I'm sure you have, because you live here longer than I have been here, but it was interesting for me to see road signs saying this area is prone to accidents. And why did they put this here? Because those signs, because accidents have happened there in the past. Now imagine if you can have a finer control over this and really monitor what is the average speed by vehicles, where vehicles are heading, how many times a vehicle brakes hard, how many times there are near misses between vehicles in a really close section of the roads, really small section of the road, maybe 100 meters. You collect all these statistics using the onboard sensors, and each vehicle will upload these statistics autonomously to a server. The server uses machine learning and artificial intelligence to identify which areas are more likely to have a specific problem. And when the driver approaches that area, it is notified by the network, look, you're in this area, these are the major problems, so be advised. And this is definitely something that is useful if you have a vehicle, a connectivity between the vehicle, an automated connectivity. Of course, everyone is connectivity when you're driving your car because you've got your smartphone. But we're talking about having the vehicle, the onboard intelligence of the vehicle talk to a server on the internet. And then the other feature that V2X gives you is being able to create a sort of local ad hoc wireless network where you exchange information with other vehicles directly, and you are not going through the network. So this is the real plus, because designing communication to the network is not so hard. We already have that. Designing communication between vehicles, this has been the trump card of IEEE so far. IEEE and ECE, in their previous standards, already have communication between vehicles, and they've always looked up and said, okay, look, you cellular people, you don't have communication between vehicles, you just have communication between vehicle and infrastructure. And what do you do if you want to tell the vehicle in front of you to brake? Do you send a message to the network will send the packet to Delhi, and then it will return back, and by the time the warning is sent to the vehicle in front of you, you crashed. Instead, we have vehicle-to-vehicle communication, so we are better. And now the cellular people said, wait a moment, now we have CV2X. Let's see if you are better than us. And this is what really, all these acronyms here are the standards that right now, today, are looking at enabling this local ad hoc network created between vehicles. So 11P, ITS G5. So 11, you may You may be familiar with this because this is the Wi-Fi standard. Indeed, IEEE, the solution devised by IEEE, is basically Wi-Fi. ITS G5 is basically Wi-Fi. Indeed, ITS G5, as you will see tomorrow, builds on top of IEEE 11p and just adds more features at the upper layers. Instead, LTE Advanced and Cellular V2X are basically the same thing. Take a different road. They have a different approach. And what are the applications that may be enabled by these technologies? They may be either single vehicle applications, so in-car content that is being received from the network. Yeah, but we don't really need V2V in this case. V2I is enough. But what car manufacturers are really interested in now, and also governments, because this is going forward, this is going to be more and more of a problem. The number of people who are injured or die on roads is a problem anywhere in the world. And having something that prevents this, that's why the government are willing to throw a lot of money on this, and why the automotive industry is willing to invest a lot. So this is really one major topic going forward in 5G. And this is even more important than machine-to-machine communication, because this is we're talking about saving lives here. So connectivity between vehicles, and this is much easier said than done. Because once you start thinking about it, beside the technological problems, you have other problems. You have one problem, which is the car manufacturers themselves. Will they have individual accident avoidance algorithms? So what happens is, if I am driving a BMW car, will I avoid crashing against other BMW cars? But if I come across a Toyota, we have different algorithms and we crash. So who's enforcing the algorithm? Even if I may have an independent algorithm, this algorithm will have to rely on metrics that are given by the car itself. What if BMW sends better metrics than Toyota? Will it mean that Toyota will crash against the BMW? So we have to standardize that as well. We need to have, and when you start telling a car manufacturer, look, your car should be sending this and this as data to the other cars, the other manufacturer car, they will say, no way I'm doing this. I am never going to tell how good my brakes are, how well my steering is. I'm not going to tell my competitor what I'm doing. And this is just one set of, we have just started with this problem, because then there are other sets of problems. Operators. So you may be driving two BMW cars, but one of them is Airtel, has got Airtel operator. The other one has got OVO. Is it an operator? Yeah, you got an operator called OVO or YO. Tell me two names of operators. Geo. Okay. Airtel and Geo. You have a BMW whose driver is using a Geo. The other BMW whose driver is using Airtel. They get close, but they don't talk to each other because they are different networks. They crash. But I say, okay, maybe BMW will just get Geo as an operator, and then you have Toyota using Airtel. They crash. There's another set of problems. You are driving to, well, this may not be a problem in India, but in Europe, we have smaller countries, and we cross the borders very easily. But operators have the coverage only in their own country. So if you're traveling between Italy and France, for example, the moment you travel, you may be coming from Italy with one operator, and you may be coming from France with another operator. They don't even talk because they are from different countries. They don't even do roaming. You crash. So, as you see, this is a problem that, although on the it's easy to say this technology will save lives. Yes, but we need more than technology. We need agreement. We need higher coordination between car manufacturers, between operators, and that's why the European Union is funding these projects where it brings together operators, manufacturers, and researchers to work away, not just in terms of technology, but on how to use this technology effectively. One example that I have not mentioned so far is platooning. Platooning is really cool once it's implemented, because it goes in the direction of self-driven vehicle, but it's also a great way for efficiently managing crowded highways. What platooning does basically is having car form groups, tightly knit groups of cars that are like joined by puppet strings, and there are the leaders, 2 or 3 cars on top of this pack, and the followers behind, and they travel at a constant speed, very close to each other, and they travel in groups. And in this way, you can manage several groups of these platoons and have platoons that go more slowly, other that go faster, and I suspect all people will want to join the faster platoons. So we may end up having very fast platoons going on highways, but this is fine, because there will be a sort of a collective ant-like intelligence governing these platoons. Here, of course, the problem will be joining and leaving platoons, because if you have this car here that wants to get out, it's easy. It will just, at the next ramp, turn left and go. If you have this yellow car here that wants to leave the platoon and get out, then you need the platoon to open up. You need to let the yellow car make the turn and get out. Again, this is fine as long as you have the intelligence and the algorithms to do it. And all this requires a group communication. So it requires vehicle to vehicle. It requires all these vehicles to talk to each other and, well, look, there's this guy who needs to make a turn, so let's open up the platoon and let this guy go out. And then we close the platoon again. And this coordination can only happen with vehicle to vehicle communication. Okay, in 5G networks, we expect to see support for non-safety V2X services, so connected vehicles, entertainment, mobile hotspot in the car, dynamic digital map update, something that I was talking about earlier. You have your digital map, and having digital maps updated, it's normally easy, but what we are looking into here is having these maps really detailed with historical data on what happened in those stretches of road, what are the likely hazards you may face on those roads. Maybe in the past that stretch of road has been known to have patches of ice form in early hours of the morning. Fine, then let the driver know about it. And then safety-related V2X services, autonomous driving, car platooning, and other safety like collision avoidance or see-through, artificial horizon. There are plenty of these related V2X services. This is the timeline of what V2X, this is just for V2X. So V2X, as you know, everything in 3GPP goes through these three phases. Phase 1, user design, use cases. Phase 2, functional description of the protocols. Phase 3, implementation. We are here, and we are almost 2018 actually. But we are in between phase 2 and phase 3. So we already have the standard. This is what I'm going to talk about today. And we are already expecting some implementation. Indeed, Qualcomm, you may know Qualcomm is a very big manufacturing company for transmitters, and they have 4G chips, and they are also building in 5G technology. And Qualcomm will have V2X, already has, as announced back in September, that is manufacturing a V2X radio to be showcased early in 2018. Okay, and in 5G and release 15, we already have, we will have the phase 3, so the implementation as well. Okay, what time do we have the break? 10:13, 15 minutes, okay. Okay, so let's have a look at the standard. Basically, when we talk about CV2X, so from the cellular point of view, CV2X is an evolution of device-to-device communication. Device-to-device communication has been introduced in LTE since release 12. And it has been perfected, and it has been adapted to V2X, so device-to-device communications for devices that are on cars, in release 14 and release 15. The idea is using a feature called PROSE. PROSE stands for Proximity Services. It was originally designed for emergency networks. Emergency networks, why? So imagine that there is an earthquake, a flood, a fire that destroys the cellular infrastructure. And you have rescue teams trying to rescue and find survivors under rubble or in a house that's partly on fire. What you need is these rescue teams to be able to communicate with people that are stranded somewhere, even though the infrastructure may have failed. So for this reason, you need device-to-device communication. That is why PROSE was introduced. PROSE has not lived an easy life, even though it was in release 12, and release 12 dates back at least 4 years. Does anyone here have device-to-device communication on their phones? No. For a very good reason. Because the operators don't like the idea of you exchanging data between your phone and your friend's phone using their resources. As we will see, D2D uses the same resource blocks as LTE, and maybe your friend is not using the same operator on his phone, but still D2D allows you to exchange the data, and this is the whole purpose, even between users that do not belong to the same operator. So the operators don't see this very keenly, and for good reasons. So device to device has really had a troubled life so far. The standard is there, but no operator is willing to pick it up. And the phones right now don't support it. But now it has found new life with CV2X, because there you see a good use case for device to device to be put into place. The idea in general is to supplement the standard downlink and uplink transfer with side link. A side link communication is a communication that doesn't go through the eNode B, uses resources that are in the same spectrum as the downlink and uplink spectrum, but they are set aside specifically for side link communication. So they are taken away from the uplink and downlink spectrum and given to the side link communication. It's called side link PC5. And V2X communication is based on ProSe. Release 12 only addressed public safety. Release 14 onward has announced D2D ProSe interface for vehicular use cases, addressing high speed, high density, and so on. The only difference between the standard ProSe and the V2X is that ProSe is nominally one-to-one and one-to-many. Vehicular communication is just one-to-many. And it makes sense, because you want to advertise your position, for example, to anyone who's in communication range. You hardly need to talk to one specific vehicle, since the network changes so quickly that by the time you've identified a vehicle to speak to for any reason, it may be gone. So CV2X is ProSe, but just for one-to-many communication. Let's have a look at the architecture. The ProSe architecture, yes. Oh, radio resource control. RRC layer is the layer above the MAC layer. What it means is that the RRC layer will be, and we will see it going forward in the next slides, will be the part of the architecture controlling the start of the D2D. So D2D is not active by itself. The RRC layer is the one that in your phone activates the data transmission with the eNode B. So every time you transmit data with the eNode B, you go into what is called the RRC connected state. It means you create a sort of stable association with the eNode B. Okay, your terminal will ask permission to the eNode B to receive and send data, and the eNode B will give permission. This is handled by the RRC layer that sits on top of the MAC layer. Okay, same goes for V2X. Okay, thanks for pointing that out. I actually skipped this. Okay, this picture shows, hope you can see it, it's a bit small, shows the architecture of ProSe. So in this presentation, I will be talking almost will be switching between using ProSe, D2D, and V2X. So what you have to remember is the standard. When you read the standard, until release 14, it was just ProSe. Proximity services, D2D for safety. From release 14 onward, it's ProSe and V2X. So even though I'm talking about ProSe, and every now and then I will switch to V2X, we are basically talking about the same thing. It's the same standard. So the standard designs since release 12 this architecture. Let's have a look. Let's try to find places that we already know. So we already know from the architecture of LTE that we have the Evolved Packet Core, EPC, that has the serving gateway, the MME, the HSS, the parts that handle, terminate, or actually acts as an anchor for the IP flows, that handles the mobility, the paging, know where you are at all times, know who you are, and so on. This is all in the Evolved Packet Core, or EPC. And we already know that the EPC is connected to the EUTRAN, the Evolved UMTS Terrestrial Radio Access Network. That is, in the EUTRAN, you have the eNode B and the terminals. On top of this, and then we also have the UE, the terminals. So these 4 blocks here are the same as you already know. But now we have some additional features. We have, on top of the UE, the so-called ProSy application. The ProSy application is not an app you can download from the Apple Store or Google Play, but it is an application layer that is already inside, supposed to be already inside the device, that communicates with the ProSy app server. The ProSy app server, as we shall see later, is the server providing all services that are related to D2D or V2X. Just to give you an example, I was talking about collision avoidance before. So if you think about collision avoidance, on the car you would have the ProSy app that collects all the data that are necessary for the collision avoidance: location, speed, heading, acceleration, brake efficiency, and it will transmit all this data to the app server. The app server, the ProSy app server, is somewhere reachable through the EPC. It's not in the EPC. It may not be even in an operator network. It may be in it's actually going to be in an independent area, not under an operator control, because this may be, for example, a server that is managed by an automobile association, an association of automobile manufacturers who are managing these collision avoidance algorithms. So you have this ProSy app talking to the ProSy app server. What will it do? Well, it will allow the communication between, it will exploit, not allow, it will exploit the communication between devices, the device to device or V2V communication, and this communication will happen over the air on an interface called PC5. Now you see all these acronyms here: PC5, LTE, UU, S1. These are standardized interfaces. It's basically the description of how two entities interact, what kind of information they exchange, what is the message flow going to be like between these two entities, what is the timing of transmission between these two entities, everything that relates to how these two entities can communicate. So what you have been, we have been covering yesterday about physical layer on LTE is the LTE UU interface. Now ProSy introduces the PC5 interface. PC5 is often used as a synonym of side link. So side link, PC5, all we are referring to is the interface between two devices that are talking to each other. Another element that is introduced in the architecture is the PROSE function. The PROSE function is seen as in a way connected to EPC. It is part of the operator network, so there is one PROSE function for every operator network, and the task of the PROSE function is to enable all the PC5 communications. So giving the authorization, providing a cryptography material to encrypt the communication on the PC5 interface, finding out which are the active user interfaces, what terminals are under coverage or out of coverage, and so on. And we will see what its function is after the break. Okay, we can have a break now. Existing blocks, EPC, UTRAN, user equipment. Now we have a new interface between user equipments that allows direct communication. We have applications that provide the services for which D2D is deployed. The applications will talk to an application server using, of course, the D2D communication, and also they will be able to reach the server through the coverage under which they are. And then there's this PROSE function whose task it is to authorize and keep track of who is using the D2D under a specific coverage. This example here is just wants to show you how you have the communication between two user interfaces. It's basically the same picture as before, but I have exploded it in some areas to show better what's inside the EPC and the various pieces, and to highlight some additional interfaces. So it's not much different from the other one. When you see PC1 here, the PC1 here is the interface between the PROSE application and the PROSE application server. It's a logical interface. It doesn't mean that they are directly connected, of course. It just means when the PROSE application wants to talk to the PROSE application server, and we will need why it needs to talk, then it will format its communication according to the PC1 format. PC3 is the interface between the user terminals and the PROSE function, and so on. This is called the architecture reference, the non-roaming architecture reference, because the two user equipments both are registered with the same operator. And then there is the case of inter-PLMN. PLMN stands for Public Land Mobile Network. It is just an acronym that identifies the network of an operator. Yes? No, it uses the LTE, the same LTE radio that you use to communicate with the eNode B. I will talk about what frequencies and what resources we are using in a while. And you will see they are the same you use in downlink and uplink, but just the portion that is set aside for PC5 communication. I'll get to that. But definitely it's not Wi-Fi. This is LTE communication. Okay, this reference model shows, for example, what is the communication between two user interfaces, so user equipment on the PC5 interface, if these two terminals are subscribers to two different operators. You can still, and the whole point of device-to-device communication is to allow also inter-operator communication. So they are allowed, according to the standard, to communicate, and this will necessarily need a few more steps, because each operator will have its own PROSE function, and PROSE function will need to talk to each other using a specifically designed interface called PC6. Why? Well, to exchange information about who's enabled for D2D communication and who's not. So if UEA wants to talk to UEB, it will need to ask permission to its own PROSE function. Its own PROSE function will scale up to the PROSE function of the other operator to which UEB belongs to see, okay, is your UE enabled for D2D? Yes, it is. Okay, and then you'll return an answer. Okay, in this picture, well, I just highlighted that 3GPP defines new reference points, PC5 between UEs, PC3 between UE and PROSE function, PC6 between PROSE functions of different operators, and PC1 between PROSE app and PROSE app server. What is the purpose of the PROSE function? The PROSE function is a logical function, and you find it in one operator. So you will have one PROSE function per operator that manages all D2D for all its own, for all the operators' subscribers. So one PROSE function for each PLMN. Again, PLMN means operator network. What are the subfunctions? What are the operations of PROSE function? It's there to provide parameters for the discovery and the communication. As I will describe in the coming up slides, two steps of D2D communication are discovery, because you need to find out who in your neighborhood is enabled, who can communicate to you with D2D or V2X. So which vehicle you have around you who are equipped with V2X. At least in the early stages of deployment, the so-called penetration of the technology, that is the ratio of vehicles that will be equipped with V2X devices, is not going to be big. So you may have 5% at the beginning, 10%, 20%, even though there is some agreement that all cars being manufactured from 2021 onward will need to have some form of V2X on board. The problem is we don't know yet which one, which will be the winner coming out of this V2X war. Will it be CV2X or will it be 11P? Still to be determined. So the parameters for used for discovery and for communication in a specific network. Then the IDs, users and managers the application IDs. So PROSE is just the technology that allows you to communicate in a device-to-device fashion, but you may have multiple applications that want to use this. So it also manages not only the single user, but also what applications are on each device that may exploit the D2D communication. And then it allows to collect subscriber data for charging. Charging is one of the critical aspects, because, okay, when I use D2D communication, can I do it freely? Or every time I use D2D communication and I move data using D2D, especially if I'm using resources of an operator under coverage, I should be charged for that. So that should go against my monthly gigabyte allocation. And the PROSE function will keep track of that. The PROSE application server, as I said before, lives outside the operator. There are several examples of application servers already. This is not new. So the PROSI application server is an example of application server that already exists in cellular networks. One example is the SMS. We've all been using SMS, texting on our phones. Texting is relying on application servers. When you send a message, this message is stored on an SMS application server and it stays there until the device of the destination device will collect it. So if you send an SMS to a friend of yours who is currently traveling by plane, so has got his phone turned off, the SMS will remain in the application server until your friend lands, turns on his phone, and will receive the SMS. So the PROSI application server is an extension of existing LTE application servers, and provides, well, the idea of what the application server will be for CV2X is not clear yet. One thing that I see is, for example, the application server may store the parameters used for collision avoidance, for example, may store the algorithms used for collision avoidance. The application server may provide several algorithms for application avoidance, and your V2X enabled car may ask for one of them to be used depending on its capabilities. So one car may be able to collect speed, acceleration data, position, but may not be able to collect brake efficiency data. So it will ask to use a collision avoidance algorithm that doesn't take into account the brake efficiency. Another car uses brake efficiency, it will ask to use this algorithm. And the PROSI application server will need to manage this different cases. How? This is all to be designed. This is all ground for research right now. So all these information, like who's using, what capabilities they have, all this will be stored in the application server. Okay, now let's look at how the communication will take place. What we have to remember is that we are looking at a different environment than we are used to in infrastructure-based communication. What you do in infrastructure-based communication in LTE is you ask for permission to the eNodeB to receive or send data. This is handled, as I was saying earlier to your colleague who's asked the question, this is handled by the radio resource communication layer. Radio resource control layer, sorry. This is an RRC task. The RRC requests permission from the eNodeB. The eNodeB grants permission. Your device, the RRC of your device, will ask for, will say, okay, look, I've got this much data in my buffer. Please give me enough resource blocks. You played with that yesterday in the lab. Please assign me a number of resource blocks to transmit the data that I have in my buffer. and it goes like this. You truly have your devices telling the network, I've got this much data in my buffer, and please give me enough resources to transmit it. Now we are looking at a different problem, because this is much wilder. We have devices that don't know about each other's existence. So first of all, they need to discover each other. So you need to have some communication in some sequence of steps that allow you to discover existing devices in your neighborhood. Once you've discovered them, then you need to communicate with them. So let's have a look, first of all, how discovery happens. Communication is relatively easy once you discover them, but discovering it is not so simple. The first step is you need to get authorization to use D2D. This is done through the PC3 reference point. So every UE that wants to use D2D or V2X, CV2X, will send an authorization to the eNode B. So before D2D, you need to talk to the eNode B. You must be under coverage. That automatically cuts off a number of use cases where you want to operate in V2V and you are in an area where there is no coverage. And this is not good. So what we are asking here is not only can I operate under coverage, but the authorization is also, will I be able to operate even when I am not under coverage? And the authorization is given usually for a limited period of time, saying, okay, I will authorize you to operate in a out of coverage situation when you are not close to an eNode B, but you are out there in the countryside or on the mountains where there's no coverage and you want to still use CV2X, but just for a limited time. Then you must go back to an area where there's coverage and obtain permission again. This is still being part of one big question mark. How long should this authorization be? Of course, it will depend on local cases. So if I am in an area where I know that coverage is scarce, then this authorization may be given for many days. Otherwise, it will be given for a shorter number of time. Why do I need authorization? Because when I am out of coverage, I can't just transmit wherever I like. I need to be given specific resource blocks where I can do the transmission. And this authorization is all about allowing devices to use these resource blocks in areas where there is no coverage, and so that at least the network maintains some form of control over who's transmitting where. So each UE asks for authorization for direct communication and for the direct discovery to the process function. Let's assume that they get it. So this is how it will happen. It will send a discovery request, first of all, asking for permission to discover who's in the neighborhood. It will send the application ID saying, I will need to discover nearby cars. My application ID identifies me as a car who wants to use collision avoidance features, for example, or as a car who wants to use gaming between cars. Maybe you have cars going on a highway and you want to play a quick game of backgammon with someone who is traveling, hopefully not when you're driving, or in a case when you are the driver is the vehicle and you are just a passenger, and the self-driven vehicle, and in this case you want to have a quick game of backgammon with someone who's with you in the platoon, and you set up a gaming D2D. So the application ID tells the network what you're going to use the D2D communication for, who you are, and the name of the transaction. So you get back a discovery response from the network. The discovery request will go all the way to the process function, and then the discovery response will come back to the device asking for, replying, okay, yes, you're authorized, this is your application code, this is the timer, the validity timer for which you will have all these features available. The first step, as I said, is the direct discovery. The direct discovery happens using a protocol that sits on top. It's an RRC protocol, so it sits on top of the MAC layer. And it happens through the PC5 interface To be precise, it uses a sub-interface called PC5D because it's still the D2D, so the direct communication interface, but here we are just using the discovery features. The purpose of direct discovery is to detect and identify UEs in proximity using direct signals. There are two types of direct discovery, open and restricted. Open just means, okay, I can be discovered by whoever. I am open to discovery. I got the authorization. Whoever wants to contact me, I am here. Restricted means I must give permission if someone wants to discover me. So it doesn't work for everyone. One interesting thing about this direct discovery is that is effectively what enables the service. Once you've given permission to be discovered for collision avoidance, then you are enabling the service at this point, and you can't refuse it. And you are going to be part of the network of cars that are using collision avoidance. Beside the two types, so in an orthogonal manner, there are two discovery modals. So the types have to do with whether you want to be discovered or not. The discovery modals, modal A and modal B, distinguish between how the discovery happens. Modal A is a sort of, I am here, I am here and I am willing to be discovered by anyone. This is something that, of course, gives two different roles to devices, because if we are using model A and these models, whether I'm using model A or model B, are mandated by the eNote B. So the eNote B may give you permission to use model A only, because it only allows model A direct discovery in its area. Or maybe, depending on what kind of application, it gives permission for model A or for model B. Model A, sorry, is one device announces its presence. Another device monitors and discovers who is there. Of course, these roles are not fixed, because the announcing UE may switch in times, may swap its role and become the monitoring UE later on. So I may go for 10 seconds in announcing mode and then switch to monitoring mode, so that I not only announce my presence, but I discover who's there. This is, if you know something about Bluetooth, this is more or less what Bluetooth does. So you have announcing and monitoring user equipment. What frequencies can be used? Now, this is a tricky problem, because remember, the frequencies are the property of the operator. And when you are given permission, the operator, as we shall see later, will tell you, okay, you want to do direct discovery, you do it on these frequencies that I'm telling you, of these resource. To be precise, the terminologies that I will introduce later is to these resource pools. The announcing UE can only announce its presence on its own operator's resource pools. That makes sense, because you are using your operator's frequencies. However, for D2D to be effective, you need to have the monitor UE not only listening to its own operator's resource pools, but also to the other operators' resource pools. So other operators who are active in that area. Otherwise, you won't discover people around you who belong to other operators. And D2D nominally allows you to talk also to other operators' UEs. So the monitoring UE can use carrier frequencies signaled by the serving PLMN. That is, serving PLMN is the one to which I am attached right now. So nominally my own operator. And other local PLMNs, other operators' networks. Model B is different. Model B is, for one thing, it's used only for restricted discovery type. So I must enable, I must give the authorization to be discovered. And the way it works is you now have two different roles, discoverer and discovery. They both have to operate in restricted mode and allow the discovery to happen for that specific purpose, whatever application they're using. And the discoverer transmits a request that is no longer I am here and the other one listens to me and discovers me. Now I am specifically asking, I would like to discover cars who are willing to use collision avoidance features. The discovery is a car who is enabled, so is restricted mode, but is enabled the discovery, and wants to use the collision avoidance features. So it will reply, say, okay, yes, I am here, I am willing to be discovered, and I am willing to be part of a network that uses collision avoidance. So you see the difference in Model A and Model B. Model A, you announce and people will just discover you. In Model B, you ask, I want these people. I want people who are, you may even ask, there's also specific parameter where you may ask for a specific car, a specific ID, because you may want to discover maybe the leader of the platooning pack. And you want to see if you are close to the leader because you want to rearrange the platoon in some way. Both roles can use, and this is a difference from Model A and Model B, both roles can use local own operator frequencies and other operators' frequencies. Again, that makes sense because when you want to discover, you need to actively get in contact with people around you. And you can only do this if you use all the possible resource pools from all possible operators in that area. Otherwise, you miss someone. Both Model A and Model B, when they finish, so when you complete the discovery, you return a match report to the process function that will authorize the communication. So once you have completed this procedure, you need to say, okay, process function, I have discovered this guy. Can we talk? Can we start communicating? The process function will return authorization for communication. Okay? The direct communication at this point can take place. So after you've discovered some users around you, you can communicate. Remember that in V2X, communication is only one to many, so it's like a sort of multicast. It can be between the group of people that you have discovered. So the standard does not tell you when you can start the communication. The standard will not tell you after you've discovered 2 devices, 2 cars, you can start communicating. It's up to how it will be implemented by the manufacturers. The truth is, it makes sense that after you've discovered, 2, 3, 4 other devices, then you start communicating with these devices you've discovered. And the communication will happen with those you've discovered only, will not be open to everyone. That's why you need to contact the process function to make the process function aware of which devices you have discovered so that the process function may authorize you and the other devices to have this communication. So authorization for one-to-many process direct communication is through the process function. And the communication is connectionless. There will be no signaling. You just send data. D2D communication uses the same LTE stack. So that you see here, the PC5U. PC5U means PC5, so D2D, but for communication. You have application, you have the IP layer, and then you have the same PDCP, RLC, MAC layer, physical layer. PDCP and RLC are the RRC, radio resource control layers. So they will just arrange communication as if you would be talking to the eNode B. They will use the same procedures at the physical layer, a MAC layer, at a RLC layer as well. And this will be encrypted as well. So members of the group will share a key, a group key. I have some slides later, but I don't think we'll get into that. We won't have time. But just to give you an idea, once you've created the group and once the Prosa function has given authorization to this group to communicate, you will also have a group key that would allow you to encrypt all communications between members of this group in a one-to-many fashion, of course. That's why you need a group key. Okay. So we've seen discovery and we've seen communication. Now we get into the problem of how we do resource allocation. The idea is there are some basic things to keep in mind. D2D uses the same frequencies used by uplink and downlink. But this has to be managed. That's why you need all these authorizations. These authorizations are there so that the network knows that there is going to be D2D communication, and the network may reserve pools of resource blocks for D2D communication. And this has to work both if either if the UEs are under coverage and they want to talk to each other, or if the UEs are out of coverage and they want to talk to each other, or if one UE is out of coverage, the other UE is in coverage, and they want to talk to each other. So there are many cases that you need to handle properly, and this will also bring up another issue that I will discuss later, that is the problem of synchronization. But let's start with resource allocation. So first of all, resource allocation, you need to be notified of what resources you are given. Normally in LTE, resource allocation happens using the physical and logical channels. Yesterday I talked just about physical channels. Physical channels tell you how you structure the bits that are used for a specific purpose and how you map them into resource blocks on the LTE resource checkerboard that we saw yesterday. So which resource blocks are for control, which resource blocks are for data, and inside the resource block for controls, which control resource blocks are used for the broadcast channel, which is used for the radio access channel, and so on. Side lane communication defines new physical channels, but also other types of channels. So what I didn't talk about yesterday is the fact that physical channels are just one type of channels. There are also two other logically different channels called the transport channels and the logical channels. The transport channels deal with what type of packets you are using, whether you're using small packets, big packets, for the information traveling on that channel, whether you send these packets frequently or just once in a while, for the communication happening in that channel. The logical channel tell you what type of information you are sending. So you see here, this is for specifically for side-link channels. The standard provides for two new logical channels called the side-link traffic channel, where you send the data, SL traffic channel, and the SL broadcast control channel, the side-link broadcast control channel, SBCC, where you send signaling and synchronization. These are logical channels. What it means is that everything that is data will go through the traffic channel. Everything that is control signaling will go through the broadcast control channel. So when you do resource allocation will go through this logical channel. Logical channels are usually mapped onto transport channels that just tell you what is the format of packets that you will be using to send this information, and then they will be mapped onto physical channels. This physical channel will insist on actual resource blocks. And you have physical channels that are specifically introduced for side-link communication. You have the side-link, physical side-link broadcast channel, PSBCH. Again, sorry for all these acronyms. Don't worry, I do not remember them myself. So just remember the idea, what the concept. Don't try to remember the acronym, because unless you do this as a living and you every day you manipulate broadcast channels, you never remember all these acronyms. The idea is important. The acronym itself is not. But the idea is the broadcast channel, the logical broadcast channel, will be mapped on the physical side-link broadcast channel. That is, you will have some resource blocks that carry all this information. The traffic channel will be mapped onto the side-link shared channel. Why shared? Just like for a normal LTE to infrastructure. You have a channel that is shared because the resource blocks are given to you now, but in the next TTI will be given to another user, and so on. So you are sharing the channel in this way. And then there are two more physical channels. There's the physical side-link discovery channel, where the discovery happens. So the resource blocks used just for discovery, to perform discovery as I've explained just now, and a physical side-link control channel, where you send control information to monitor the quality of the communication. So this is the channel where you get, it's equivalent to the physical control channel in LTE, where you send back a feedback to the user, to the UE or to the eNode B about what the communication was like in the opposite direction. Resource allocation happens in two different modes, called the scheduled and the autonomous mode. In schedule mode, the eNode B indicates what physical resources are used, should be used on a UE specific basis. So in schedule mode, the eNode B will tell, okay, you communicate using this resource pools. Every time you send something to your group, you just use these resources. You instead will use this other set of resources when you send something. In this way, you never have a conflict. This is what the automotive manufacturers like, because one thing that they don't like about, and I was discussing this with some of you earlier during the break, the reason why the automobile manufacturers did not pick up on IEEE 802.11p or the ECE ITS G5 standards is that they are random access technologies. So you never know if you end up colliding, not in terms of vehicle collision, but packet collision. You're going to collide because 802.11p is like Wi-Fi, is based on CSMA, is based on carrier sense multiple access. And you have packets that collide, just can't be helped. So they don't like the idea of relying on a technology where there's too much randomness. But they like this. They like the schedule mode in CV2X, because the schedule mode allows V2X communication, and it provides sorry, I'm missing the word. It provides an division, a differentiation of resources between user interfaces, between user equipment, between cars. So one car will use some resources, another car other resources. There will never be a conflict, and all cars will listen to all the resources, all the resource pools that the other ones are using. This one works fine if I am under coverage. Indeed, the UE must be in RRC connected mode. RRC connected mode means you must be connected to the UE, to the E node B. So the E node B gives you every time what resources you can use. It may say, okay, for the next 10 TTIs, you will use these resource pools for D2D communication. Then come back to me and I will tell you what to use next. So you are tightly monitored. And the UE sends scheduling requests to the node B just like it does for infrastructure communication. It sends this sidelink buffer status report saying, I've got this much data that I need to send using D2D. And the E node B will tell the car, okay, good, use these resource pools for your data, and then come back to me when you need more. And I will give you the permission to use other resource pools to communicate. The other mode is autonomous mode. In autonomous mode, the UE is on its own, and this needs to work when you are outside coverage. When you are outside coverage, you can't have a E node B telling you which resources you can use on a TTI basis. You are on your own. So all the E node B can do is, okay, as you are traveling in an area without coverage, please use these resource pools and just these resource pools. So in a way, the E node B gets some control, knowing that in areas around it where there is no coverage, it still has some management of who's using which resources. But it doesn't have the day-to-day or the moment-by-moment control of who's using resources at a specific time. There, you may have conflict. And this, again, is something that the operators don't like. Because the operators don't like, not the operators, sorry, the automotive manufacturers. Every time you tell them, okay, there may still be the chance that they are using the same resources. Why are they using the same resources? Because once you are out of coverage, there's no way you can tell all the users, all the cars out of coverage to use a different set of resources. You just don't have enough. You've got to, at some point, reuse some resource pools for cars that are out of coverage, so that you may have 3, 5, 30, 10, 100, who knows, cars who are allowed to use the same resource pools. That's something that can be helped. So it works outside coverage or in case of network failure. When you're out of coverage, one thing we have to address, and we are going to talk about this in the next slides, is synchronization. So you need, when you're out of coverage, you need to have a synchronization source. Why? Well, for all the purposes of synchronization, you need to know when a subframe starts. You need to know where to find the pilots. You need to know which number of frame you are. Every subframe is numbered. The number of frame is used by the encryption algorithm. Indeed, when you are using LTE or even 3G or 2G, every data you send out is encrypted using not only a key that is new for encrypted not only using a key that is new for your data session at that time, but is encrypted also using among other things, the frame number on which the data is being sent. This allows for encryption keys that change every time, and so you avoid replay attacks, and this makes the whole structure much more robust. So you definitely need to know what is the frame reference that you have, and I will talk about this later. What are these resource pools? Resource pools are used from the same resource blocks that you have in LTE, in normal use in LTE. So to be precise, resource pools are carved out of the uplink resource pool, of the uplink resource blocks that you use in LTE. They are, if you remember, I showed it briefly yesterday. If you remember how the resource blocks are structured in the uplink, you have the outer edges of the spectrum for uplink. You have the control channels, the PUCCH, physical uplink control channel. They are here and here. These are used for giving feedback to the eNode B. The way resource pools are reserved for D2D communication is the eNode B will tell you, look, this is, okay, let's take it from even before going into these details. The eNode B will tell you in the sequence of subframes which subframes can be used for D2D and which subframes can't be used for D2D. So it will first of all provide you with a bitmap that basically says, okay, starting from now, the next subframe may have some resources set aside for D2D, the following one as well. The next one, no. The next one just can only be used for uplink standard communication, only standard communication, again D2D, and so on. Inside a subframe that can be used for D2D, there are still some resource blocks that can be used for uplink cellular communication, but you carve out two sections that are the resource pools, that contain the resource pools assigned to D2D users. So resource pools are a set of resources that are assigned subframes and resource blocks inside the subframe. There's a subframe bitmap indicating which are the subframes you can use for D2D communication. And inside a subframe, you use two resources that are basically two frequency bands, these two frequency bands here. And you will be given the number of basically the subcarrier where this block starts and how many of these you have. So in the advertising information that is given by the E-Node B. The E-Node B will give you the PRB start, the PRB end, and the PRB number. And this automatically outlines these two. So the PRB number is the same. So these two sections are of the same size. Will tell you how many subcarrier you can use, starting from which subcarrier and ending to which subcarrier. As you see, it's very easy to control exactly how many resources you are setting aside for D2D communication and how many you are still using for uplink communication. The E-Node B in this way has a very tight control of how resources can be used at any time, both for cellular communication and for D2D. There may be two types of resource pools that are associated to transmission and reception. So I may tell one user, look, you can use these resource pools for transmission and you will use these resource pools for reception. Of course, to another D2D user, you will tell, you will use these for transmission and the other ones for reception, because you need to have people listening to each other and talking to each other. So you need to organize how they are hearing and listening to each other. And these resource pools are advertised using system information blocks. What are system information blocks? If you remember, one of the things I told you yesterday is that after you have synchronized to the E-Node B, you will first of all detect a block of resources where you have the so-called master information block that tells you what are the parameters that are in use in the cell, which subcarriers are used for uplink and downlink, and so on in that cell. The master information block also points you to other parts of the checkerboard where there are specific system information blocks that give you additional information. The standard has introduced 3 new system information blocks, number 18, number 19, and number 21, where these side link information is stored. So in these side system information blocks, once you connect to the E-Node B, you get to know which resource pools are used for discovery, which resource pools are used for communication. And the resource assignment happens in 4 possible ways. They are called Mode 1, Mode 2B, Mode 3, and Mode 4. Mode 1 is resource pool assigned for autonomous allocation for discovery. That means when you are not under coverage, you are given some resources that you can use to discover other users. And when you are under coverage, you use Mode 2B, scheduled allocation for E-Node B. This happens on the physical side link discovery channel. Mode 3 and Mode 4 are used for communication, and this is the allocation that is done either under coverage or out of coverage. But we have seen this already, basically. This advertisement happens, as I said, using this MIB and SIB. I will not go into details on how, where they are placed. The master information block is repeated periodically. It gives information on how the communication in that cell is structured, and it points toward other parts of the checkerboard, other resources in time and frequency, where the terminal may learn about what it wants to do. If I want to do D2D, it will point to system information blocks with the resource, where the resource pools are announced. As I said, system information blocks introduced specifically for side links are these 18, 19, and 21. For example, System Information Block 18 carries a number of additional information. For example, it may list up to 16 resource pools, so it will tell you where to find them, in which frequencies to find them, where the UE is allowed to receive sidelink transmission, and then it identifies a number of resource pools that can be used for transmission when the UE is out of coverage. Why are they advertised in this way? Because in this way, the eNode B just tells the UE, okay, if you get out of coverage, remember that you can use only these resource pools to communicate with somebody else. It also has all the IDs of in-coverage UEs that are enabled to use D2D and V2X, and this can be useful for discovery. This advertisement also has a validity time. The System Information Block 21 has additional information just reserved for V2X communication. So frequencies that are only reserved for cars and not for other, like normal safety-oriented communication. It also has information on how to compute the channel busy ratio for congestion control. You will see why this is important tomorrow when my colleague talks about the channel busy ratio computation in V2X. So I'll leave it for later. Okay, let me skip to the last topic that I want to address today is synchronization in D2D. Synchronization, like I said, is important because you need to know the structure of the subframes, where they start and how you can interpret what's in there. Normally, when you are under coverage, you are synchronized to the eNode B. The eNode B gives you the synchronization. When you move from one eNode B to the other, you synchronize to the new eNode B. Ideally, all eNode Bs are synchronized between themselves, so that when you perform a handover, you don't mess things up just because you one eNode B is 2 milliseconds ahead of the other one. But when you have out of coverage communication, that may not be so easy. So synchronization is done normally in LTE by the UE tuning to set frequency that is valid for all LTE cells, where you find the so-called primary and secondary synchronization channel that provide the synchronization. So they provide the timing that is used by that UE. This is when you are connecting to an eNode B. In this way, you discover what is the physical cell ID. You can do this by looking at how the pilots are structured, what are the sequence of bits that the pilots are sending, the time slot and frame synchronization, and so on. If the UEs are that want to communicate are in coverage of the same cell or even of two synchronized cells, you have no problem. You just have to balance to control the propagation delay and the timing advance, but this is easy. When one or both the UEs are out of coverage, then one of them needs to have a so-called syncref UE. Specifically, the one out of coverage will need to find a terminal that it can use as a reference. In the standard, this is called a syncref UE, a user equipment from which I get the synchronization. And I need to know who it is, and he needs to know that I am getting a synchronization, because we need to be on the same page when we exchange data in D2D fashion. when you act as a syncref UE, so if you want to become, if you are a user equipment, if you are a car out of coverage, and you want to become a syncref UE, and nominally all cars, when they are out of coverage, try to become a syncref UE, but only one of them will succeed in doing so, and there's a protocol for establishing who is the syncref UE. But when they do this, they will advertise two pieces of information. They will advertise their ID. The ID is a number, a local number to identify themselves in the local group of D2D communication. This number is an 8-bit number that by convention, if the UE is under coverage, it will select a number between 0 and 167. If the UE is out of coverage, it will select a number between 168 and 335. No, so it's not 8 bits. It's more than that, because 8 bit will be 255. But it's 335 out of coverage. This ID is used for the protocol that determines which UE should become the syncref UE in a group of cars. Also, it will broadcast its own master information block that, among other things, has a flag saying whether the car is in coverage or not. So the case could be one car is under coverage, the other car is out of coverage, but they can communicate with each other. So one will say to the other, look, I am out of coverage, I want to be your syncref UE, and I am getting my synchronization from the UE, so you can trust me. And the out of coverage car will say, okay, fine, I will use you as a syncref UE. This number here is used so that this car knows that it will need to always synchronize to whoever is broadcasting that number once it decides to get that as a syncref UE. Now, the point is, when will a car want to become a syncref UE? Because you see, if you are inside the coverage of a node, an input B, that doesn't necessarily mean you may not act as a syncref UE for an out-of-coverage car. But if you hear the input B very well, likely you are far from the cell edge. So you are not really likely to become a syncref UE because you are far from the cell edge, and you will never be able to hear someone who is out of a cell edge. So that won't work for you. Instead, if you are close to the cell edge, likely the power of the E node B will be received much more weakly. So in this case, you may want to become a syncref UE. So the standard provides for an algorithm that says if the power from the E node B is below a threshold called sync-TX threshold, then you will start advertising your willingness to become a syncref UE. Otherwise, you don't do it. If it's above threshold, then you don't transmit any sync information. Why? Because it's useless. Because likely all the cars you can reach in D2D communication will also be under E node B coverage, so they will need just the E node B to synchronize. If you're out of coverage, then you will look for a suitable syncref UE. Which one will you use? First of all, you will listen to cars around you who are sending out a syncref UE, or sending out a signal saying, I want to be a syncref UE. And you, as a car, will partition these other cars in three groups. Cars that are in coverage. How do you know that? Because if a car is in coverage, and this is the case of this police car here, for example, a car is in coverage and is advertising that it wants to become a syncref UE. And it's very reliable because it is getting its own synchronization from the E node B. Or UEs whose ID is between 0 and 167. It means that this car may not be in coverage, but it is receiving the synchronization from another car who is in coverage. And then there's a third group, all the other UEs. That is UEs that do not advertise to be in coverage and whose ID is higher than 167, because it means that they are not even receiving their own synchronization from another car, from a car that is under coverage. Let me just walk you through this example to understand how this works. Imagine that you have this situation where you have an E node B and you have one car in coverage and other cars who are not in coverage. How do they manage the syncref between themselves? So clearly the green truck will sync with the E node B because it's under coverage. And it will advertise, I am in coverage, and it will pick an ID between 0 and 167 to be identified as a possible syncref by other UEs who are in coverage or out of coverage. If you are in coverage, of course, you will not need to pick this one. But this red car, who is out of coverage, needs to find a syncref. Which one will it choose? Well, by listening to its neighborhood, it will hear that there's a car that is not in coverage, this one, and a car that is in coverage, that claims and advertises to be in coverage. So it will establish a side link with this one, having the green truck as a syncref. So it will align its own subframe reference to the same reference of the green truck. Then it will start advertising to become himself a syncref, saying, I am not in coverage, my syncref ID is 55. As you notice, it's the ID of the green truck, because the procedure is if I get the reference from someone who is under coverage, then I will copy its ID. Why do I do this? Because the black truck listening to the red car will know two things. Will know that the red car is not under coverage, and it sees that from the MIB advertised by the red car, but will know that the red car has a reference from someone who is under coverage. So it is somehow trustable. It will then get the reference from the red car, and it will advertise himself as a syncref for other cars, but it will advertise that is not under coverage, and it will pick an ID that is the number advertised by its own syncref, the red car, 55, plus 168, 223. So 233 means, for whoever is listening, in this case the gray car behind, the gray car behind will hear the advertisement from the black truck only, will not hear the red car. The green car the gray car will understand this. It hears an advertisement from the black truck. The black truck is not in coverage. The black truck does not receive the reference from someone who is in coverage. Why? Because its ID is higher than 168. So, okay, I will use the black truck as my sync ref, because from where I stand, from where the gray car stands, that's the only choice. It receives a synchronization that is third hand, but it's still better than nothing. If the gray car accelerates and passes the red truck, it will get close to the red car. And if it gets close to the red car, now in its neighborhood, it will hear someone whose synchronization is more reliable than the black truck. Why? Because it sees an ID that is lower than 168. So we'll know, okay, I will get this guy because this guy has a better synchronization to the inode B, so that when I go into the inode B, I will be more tightly synchronized to the inode B. Okay, so it's a bit tricky, but it's a nice protocol that allows you to find at all times what is your best reference, knowing simply by an advertisement, a flag, and an ID, what is the situation you're dealing with. What about the ambulance over there? The ambulance in the back doesn't hear anyone. It's too far from anyone. So what it can do is just advertise himself as a possible sync ref, picking a random number above 168, and not advertising to be in coverage. So anyone who is between the gray car here or the ambulance here, which one will it pick? It will pick as a sync ref the strongest signal. If it's close to the gray car, it will pick the gray car. If it's close to the ambulance, it will pick the ambulance. If it's closer to the ambulance, and here both of them, it will pick the ambulance. Because to this guy, picking one or the other makes no difference. I am either choosing between a third and synchronization or someone who doesn't have a synchronization in any way, so I might as well just go with the strongest signal. Okay, I guess time for some questions. Oh yeah, the number of bits is actually what I guess it's 9. What you see in the standard is just these two numbers: 0, 167, 168, 335. So it will need 5 bits, of course, at least 5 bits. I guess the standard, I don't know why they picked this number. Frankly, I don't know why 335. It's just such a weird number, but it's there. Why 168? I don't know. It's there. So there must be some hidden reason that sometimes this number are the a compromise selection between different interests. So I don't know what's behind this. Other questions? Okay, so thank you for your attention today. I will close the class. I guess this afternoon you'll have some labs on D2D, right? Okay, I will be there also like yesterday, so if you have more questions, feel free to ask.